Okay, and let me share my screen with you. Canvas screen, that is. And by the way, I was not able to post yet your detailed schedule. I will post it here as an announcement. That way, everybody will be constantly reminded of the synchronous and the asynchronous schedule. So your synchronous would really be as required. We will meet each other face to face here online. The asynchronous may be for feedbacking and can be converted to synchronous on a case-to-case basis as the need arises. For the dry lab, it's really asynchronous, wherein you'll be given exercises to process, to answer, and then submit also at the end of the period. So I will place the announcements later when we're done already. And I will also ask you to group yourself. So I will just place 2 announcements after the class regarding that. Okay, I'll go to modules. By the way, class, just in case I have missed to mention this, you cannot access Module 1 if you haven't finished everything that is required in Module 0. It's the same through with the other modules. You need to be able to do the to-do list or accomplish the task in the previous module so that you can move forward to the next module. That was set as a prerequisite for it. So you may wonder why you may not be able to access the lessons or any to-do tasks in module 1, primarily because maybe you haven't done the to-do in module 0. That would be the same for the other modules. So for today, we'll hear in the introduction to heat transfer. So let me click on this. I think I placed here a downloadable, as I was not able to place in here. Let me just, if I can, I will place here the downloadable equivalent of this particular module, the intro to heat transfer. So we're going to start with the basics of heat transfer here. So we know that heat by definition is the energy in transit. So it cannot be contained in one particular location, but it is always in transit dynamic and is always in transit. This is primarily because its driving force is temperature difference. So it's constantly in transit because of the temperature difference in bodies or objects. So whenever exceeds the temperature difference in a medium or between media, heat flow, there must be. So different types of heat transfer processes are called modes of heat transfer. So when we speak of modes of heat transfer, then we are referring to the 3 common known modes of heat transfer. Actually, there are 3 only. We have the conduction, convection, and radiation. So these modes are shown below in the figure. So when a temperature gradient exists in a stationary medium, even if the medium or the object is not moving, which may be a solid or a fluid, heat flows under the law of conduction, heat transfer. So in conduction heat transfer, there is really no need for your medium or for the object to move. It can be transferred through by virtue of transfer of heat through the molecules. So on the other hand, if the temperature gradient exists between a surface and something that is moving, a gas or a liquid, a liquid, so a moving fluid, then the mode of heat transfer for that is convection. So conduction is for solids, stationary. Convection is maybe for a non-moving object and a fluid flowing past against it. So that's convection. Now, the third mode of heat transfer is termed radiation, and it needs no medium. So no medium to transfer through since it is driven by electromagnetic waves. Now, these waves are constantly emitted from all surfaces of finite temperature. So there is a net heat transfer by radiation between two surfaces at different temperatures. So even if the two surfaces are not in contact, they remain stationary, it's still possible for heat transfer to occur via electromagnetic wave emission or electromagnetic waves emission. And that mode of heat transfer is what we call radiation. So the picture representation of the three modes of heat transfer is shown here. We have conduction in the case of this slab or solid in this direction. So we are to assume, actually it's not to be assumed because it's written here already, that since the direction of heat flow is from T1 to T2, or from this side to this side, then T sub 2, T sub 1 must be greater than T sub 2 in this case. So T sub 1 is greater than T sub 2. Now in convection or convective heat transfer, you have a moving fluid here. It could be a liquid, it could be a gas, and this is your solid that is not moving. So that's convection because you have the movement of this particular medium. In the case of radiation, there's no movement at all, but still heat is transferred to the surfaces by the emission of electromagnetic waves. So let's go to each of these particular modes of heat transfer, and we'll go to conduction first. Let me just enlarge this one. Okay, so when we speak of conduction, so it's the mechanism of heat transfer whereby energy is transported between parts of a continuum by the transfer of, so what is being transferred? Kinetic energy between particles or groups of particles at the atomic level. So we can view in the case of heat transfer by conduction that the transfer is in the atomic level, or it starts at the atomic level. So we could, or we should conjure up the concept of atomic and molecular activities in this case. So in gases, conduction is caused by elastic collision of molecules. Consider a gas in which there exists a temperature gradient and assume that there is no bulk motion. So the gas may occupy the space between the two surfaces, which are maintained at different temperatures, as shown here in the figure below. So we associate the temperature at any point with the energy of the gas molecules in proximity to that particular point. Now, this energy is related to the random translational motion as well as the internal rotational and vibrational motion of the molecules. So the transfer of heat is really by virtue of the motion of the molecules. Now, shown here in the figure, the hypothetical plane at XO is constantly being caused by molecules to move, or constantly being crossed by molecules from above and below due to their random motion. Now, however, molecules from above are associated with a larger temperature than those from below. So temperature above is greater than those below. Now, whenever there is a change or a difference, rather not a change, a difference in the temperature, then there is also heat transfer. Now, in the positive direction. So we may speak of a net transfer of energy by random, take note, molecular motion as a diffusion of energy in the case of conduction. Conduction, as we have said, happens in solids. So how can then be heat from one side of a solid transferred to the other side? So it's through the random motion of the molecules of that particular solid. So still driven by what we call temperature difference. Now in liquids and electrically non-conducting solids, it is believed that to be caused by longitudinal oscillations of the lattice structure. It is called also lattice waves. So it's possible for liquids and electrically non-conducting solids to still have, shall I say, experience conduction through what we call as the transfer of energy in the lattice of the material. It is through what we call lattice waves. So thermal conduction in metals occur like electrical conduction through the motion of free electrons. So thermal energy transfers occur, or rather transfer occurs in the direction of decreasing temperature, a consequence of the second law of thermodynamics. So I think this one is already shown here. So the transfer is from a higher temperature side to the lower temperature side. Okay. Now, in solid opaque bodies, thermal conduction is the significant heat transfer mechanism because no net material flows in the process. Now, with flowing fluids, thermal conduction dominates in the region very close to a solid boundary. So between fluids, let's say, for example, you have a gas and you have a liquid, so between two fluids. So thermal conduction dominates in the region very close to the boundary of the between the two fluids near the solid boundary. Do you understand this one? So with flowing fluids, take note, thermal conduction dominates in the region very close to a solid boundary. See, if I go back to my example, if I have, let's say, for example, let's say my other fluid is steam and another fluid, which is, let's say, water, example lang. So how would you explain this particular thing that is stated here, wherein the thermal conduction between these two fluids that are not in direct contact can, as it says here, dominates in the region very close to the solid boundary. This is in the case of what? Or where can you see this particular phenomena, or where could this particular phenomena be observed? Like gas and, let's say, water, or steam and water. Then you have this dominating region of where thermal conduction is happening in the solid boundary. So what does this mean? Or anybody here who understand what does this mean? So it says here where the flow is laminar, referring to the region very close to the solid boundary and parallel to the surface, and when there is no eddy motion. Where there is no eddy motion, meaning there's no eddies, or there are no eddies on the solid boundary. What do you think is meant by this? So there could be thermal conduction between fluids. So we thought all the while that conduction can only be in solids. So where can conduction in this case happen? So I gave you two fluids, let's say steam and liquid water. So where can you apply this? What particular scenario can you give me as an example for this? Let's say, for example, you have a stirred tank heater. So inside that heater is just example lang maning ako niya ha. Let's say inside that stirred tank heater is water, pure water. Since it's a stirred tank heater, of course, we have in mind that that particular water inside the tank will be heated. So the heating medium is steam. And steam is flowing inside heating coils. We call them heating coils. So your steam is your heating medium for the water inside the tank. So it says here that thermal conduction happens between the water inside the tank and the steam inside the coil. Now, the dominating part where thermal conduction occurs is in the boundary. So meaning is in the boundary of the liquid water and the steam, and that boundary is referring to the coil where your steam is flowing inside. So amo ni siyang ginanamin sini. With flowing fluids, thermal conduction dominates in the region very close to a solid boundary. So hindi man ta pwede kahamba conduction nga ang duha ka fluid nagmix na or nagkit-anay gid. So there has to be a solid boundary between the fluids. So I gave you the example of liquid water and water vapor. So in the case of heating, so the solid boundary there is your coil, the coil where your steam is flowing inside. Okay? Now, examples of conduction heat transfer are tremendos kadamo. So on a summer day and a day-to-day observable phenomena, there is a significant energy gain from outside air to room air. This gain is principally due to the conduction heat transfer through the wall that separates room air from outside air. So you have a fluid which is outside air and another fluid which is room air. But you may wonder why. How come if it's very hot inside, you also later on feel the warmness inside? That's because of conduction transfer in the boundary, which is the wall of the house. So also in electronics, so if there's a computer engineering student here or an ECE, they will relate with this. Of course, you can also relate. Also in electronics cooling, process conduction is a heat transfer mechanism used in every electronics design. Even if a system is designed for convection cooling of the circuit boards, conduction is still, take note, dominant heat transfer mechanism between the component devices and on the circuit board. What does this mean? I think everybody, even if you're not an ECE, you know what a circuit board is. It has a lot of elements in there, and there are elements that really generates heat in the process. So how is this particular element continuously, shall I say, maintained in its, let's say, maximum allowable temperature? So what happens is, since your particular circuit element is in the circuit board, the energy that it has over time will increase and it is being transferred through the circuit board itself. So the cooling there is not just a process of convective cooling in the case of there is a fan, or I say all electronic devices I think have some form of fans for convective cooling, but also conduction in itself helps in the cooling of such particular electronic devices. Why? Because the elements in themselves in the electronic board is also transferring their excess energy to nearby elements or to the board itself, which is of lower temperature than it is. So conductive heat transfer siya. So we cannot just limit saying that it's just convective heat transfer that ensures that no circuit element will melt over time in prolonged use due to prolonged use, but also conduction helps in cooling them down. So amo ni siyang gina-mention diri. So we have the notion nga ang nagapabugnaw na siya ang fan kay kung wala na siyang fan mainit kina siya, but nonetheless it's being stated here that conduction, also heat transfer, is happening within the board itself, the circuit board itself. So this is especially true for power electronics where concentrations of heat are developed in the components such as power silicon and magnetic. This heat must be transferred via conduction to the component case, the circuit board, or a heat sink. It can be handled by the system level cooling mechanisms. Consequently, all electronic designers must be aware of the techniques of thermal conduction and its analysis. So it's actually a help between convective cooling and conductive cooling. That way, these heating elements or elements that will over time be heated rather, due to prolonged use will still, let's say, not melt or will not damage the entire board itself. Although I think the very purpose of the fans inside these electronic devices, it will also aid in heat transfer. Most of the time, our computer, I think I have experienced it myself. It will not, shall I say, power up or boot up, whatever is the term there, whenever my fan is not working. So I have experienced it myself. Why is it that it will not turn on? It's because the fan is not working. So in itself, it guarantees that there won't be any melting in my circuit board or any circuit element, because the system in itself checks that since the fan is not working, and there will just be purely conductive cooling that will happen if the computer will be turned on. So it tells you, it more or less tells the user that no, you have to check your fan because it's not working and the computer will not turn on. Okay? Now, related to conduction is the Fourier's law. I'm not sure if this was discussed partly in your physics, but Fourier's law is being used rather in conductive heat transfer or in the mode of heat transfer, which is known as conduction. So it is possible to quantify heat transfer processes in terms of appropriate equation or rate equation. And this rate equation gives you the derivative d capital T dx. How will temperature change as the distance in which we're going to measure that particular temperature is reference to a particular starting point. So x is that particular distance from the starting point where heat is to be transferred. So it's actually due to temperature difference here. So these equations may be used to compute the amount of energy, and that is the Q. And it has a subscript x here because the direction of heat transfer is in the x direction. So whereas these equations may be used to compute the amount of energy being transferred per unit time. So this is actually energy per unit time, okay, the Q. Now, the rate equation is known as the Fourier's law. Now, Fourier's law is a phenomenal that is law that is developed from observed phenomena rather than being derived from principle. Now, the general rate equation is based on experimental evidence. So the reason why we have this particular equation relating rate of heat transfer to rate of temperature change in the x direction is because of the experiments that were done over it. So for a one-dimensional plane shown in the figure, so if this is our one-dimensional plane, having a temperature T in the direction of x, so meaning T here is measured in the x direction, and this x direction is the horizontal direction. The rate equation is expressed as Q sub x is equal to negative K d sub T or d capital T dx, no, not sub T. So heat flux, the Q, which is the heat flux, has the unit watt per square meter. Now we know for one that the watt is joule per second. So the joule per second is the rate of the transfer of energy, which is in the form of heat. Now, it's already the watt in here in the numerator. If this watt unit is divided by, let's say, for example, 1 square meter of area, then you're measuring what is the heat transfer rate in that particular 1 square meter of area, which is referred to as the heat flux. Now, this is the heat transfer rate in the x direction per unit area. So mentioned already, perpendicular to the direction of transfer. I think this was mentioned in your differential equation. I'm not sure if we had discussed heat transferred or we took it away from the topic because other programs will not anymore have it discussed. But in the time wherein it is included, it's also mentioned there that your heat flux is the heat transfer rate per unit area, which is perpendicular to the direction of heat transfer. Okay, this Q, referring to the heat flux, is proportional to the temperature gradient. This is your temperature gradient, specifically derivative, because it's per dx. X is in the horizontal direction. The proportionality constant K, you know already, is what we call as the thermal conductivity, and is the characteristic of the material. Materials may have low thermal conductivities over the other, and it will have a great influence on the amount of heat that could be transferred through that particular material. And it is a characteristic of that particular material. Now, why the minus sign? So the minus sign is a consequence of the fact that heat is transferred in the direction of decreasing temperature. Decreasing temperature because heat cannot be transferred from a low temperature region to a high temperature region. You cannot give what you don't have, just like what we say. So it's the same thing. How can heat be transferred from a low temperature region to a high temperature region. So it has to start from a higher temperature to a lower temperature. And since the difference in the temperature would be negative, so T sub 2, for example, will be less than T sub 1, then to compensate for that so that we will have a magnitude of heat flux which is positive, there is a negative sign in here. So the minus sign is a consequence of the fact that heat is transferred in the direction of decreasing temperature. Under the steady state condition that is shown here in this figure, where the temperature distribution is linear, the temperature gradient may be expressed as, so this temperature gradient may be expressed as T sub 2 minus T sub 1, which is the difference in the temperature, divided by the L. This is your L, okay, the thickness of the material itself. And the heat flux could be written in this form. So now we have eliminated the temperature gradient here, d capital T dt, to this particular expression. And this is now our heat flux. Note that this equation, referring to this one, provides a heat flux that is the rate of heat transfer per unit area. The rate of heat transfer per unit area is known as the heat flux. So the heat rate by conduction in watt, which is joules per second, through a plane area A is then the product of the flux and the area. And as such, you have this. So if you want, class, if the problem is really just asking you for the rate of heat transfer, the answer in this particular equation, which is heat flux per unit area, should be multiplied to the area. What would that area be? Again, we go back here. That area will be the perpendicular area in the direction of heat transfer. So in our illustration, that area would be this face. Okay? There are problems that are asking for the rate of heat transfer, not the heat flux. So if it's the rate of heat transfer, solve first the heat flux using Fourier's law, and then multiply it with the cross-sectional area perpendicular to the direction of heat transfer in this case. Very easy because you have encountered it, I guess, in your physics, and hopefully we did not took it out in DE. Now we go to convection. Okay, 1204. This mode of heat transfer involves energy transfer by fluid movement and molecular diffusion. So if conduction is through molecular energy transfer, it could be random molecular movement or translational motion, rotational motion, anything that is associated with the motion of the molecules. In this case, convection would be really requiring that there is fluid movement and molecular diffusion, something to diffuse through a given, let's say, diffuse through a, they refer to that as stagnant set of molecules. It need not really be moving, but this particular fluid need to diffuse through those particular set of molecules. Now, consider heat transfer to a fluid flowing over a flat plate as in the figure here. If the Reynolds number is large enough, 3 different flow regions exist. You're done already with your momentum transfer. I think you're done already with momentum transfer, and you already have the idea of what is Reynolds number. It tells you whether the flow is laminar or turbulent. So with the Reynolds number, there is this region that exists. So you have the turbulent region, you have the laminar region here. So there is not much eddy here because the flow here is laminar. This is the turbulent. And this is, I think, the region that is referred to the transition part. But when we use Reynolds number, there are only 2 flows that we are classifying. And that's your laminar, of course, and turbulent flow. So immediately adjacent to the wall is the laminar sublayer where heat transfer occurs by thermal conduction, which was mentioned already on top. So outside the laminar sublayer is a transition region. So this is really the region in between laminar and turbulent we call the buffer layer. So take note of this term, where both eddy mixing and conduction effects are significant. So this is where you're going to start to see eddies forming. Beyond the buffer layer, which is the transition between laminar and turbulent flow, is the turbulent region, where the dominant mechanism of transfer is eddy mixing. So there is actually turbulent motion because there is already what we call eddy mixing. What about convective heat transfer? So heat transfer by convection is described using Newton's law of cooling. So in here, you'll be using the H already, not the K, which is the heat transfer coefficient. So it's a constant. And your formula for heat transfer this time, it's really heat transfer in watt, meaning joule per second set of units, is H times A times this difference in the temperature. The wall temperature in Kelvin and the free stream fluid temperature, which is the is also in Kelvin. Now, this is class, by the way, fundamental, shall I say, generic form of convective heat transfer rate equation. But each of these modes of heat transfer, we will really study in detail. So the first one is conduction, followed by convection. So I'm only telling us early as now that this is the generic, general form of convective heat transfer equation. But when we speak of specific convective equations for different surfaces and fluid combination, this may vary. Okay, so if you have, let me just mention it, if you have a book, or in this, even if it's just a soft copy by Gian Kuplis, Transport Phenomena by Jan Kuplis, or Transport Processes and transport phenomena, basta Jan Kuplis ang author, you will be able to see the different classification of convective heat transfer, even conductive heat transfer. So it's not just when we say conduction, isa lang ka klase, or when we say convection, isa lang ka klase. Damo-damo pa na siya na-classify na klase sa convective heat transfer. Also dependent on some equations also being dependent on empirical data. So some equations, just like this Fourier equation, which came up through experiments, are also empirical in nature. Ang mga equation nga gamiton sa convective heat transfer. So the last mode of heat transfer is radiation. Radiation, the mechanism of heat transfer by radiation depends on the transfer of energy between surfaces by electromagnetic waves in wavelength interval between 0.1 to 100 micrometer. So radiation heat transfer can travel in vacuum, such as solar energy. So what's so unique about radiation is there is no really contact between solids and fluids, between fluids, because it's really through electromagnetic waves. So even in vacuum, radiative heat transfer can occur. Actually, it's the only mode of heat transfer that can occur in vacuum. So radiation heat transfer depends on the surface properties such as color, surface orientation, and fourth power of the absolute temperature T on the surface. It's already stating here what could be found in the formula. So the basic equation for radiation heat transfer between two gray surfaces is given by this one. So your what symbol is the sigma? Sigma, the Stefan Boltzmann constant. It's a constant. By the way, class, this is 10 raised to negative 8. Okay. Emissivity of the surface, it's a characteristic of the surface which provides for how effectively a surface can emit energy relative to a black body where there's no reflection, and it ranges from 0 to 1. So the value of the emissivity will only be from 0 to 1. It cannot be negative. It cannot be greater than 1. So it's the property of the body. The F is the geometrical factor which depends on the orientation between surfaces. Actually, in physics, there's no F anymore. But this is just assume that the F has negligible effect on the rate of heat transfer via radiation. So these are the three formulas that you are to take note in terms of the three modes of heat transfer, and we'll be visiting them again when we go to the specific modes of heat transfer individually. Okay, the last thing that you need to know about this particular module is how to write the energy balance equation with heat generation. Meaning, what if the object or the material or the body is generating heat in itself? So this could be probably observed through if there's a chemical reaction that is occurring. So there are chemical reactions in which heat is being generated. The reason why some chemical reactions have to be placed in jacketed reactors, it's because they generate heat. So there has to be an energy equation, balance equation, which accounts for the heat generation. Kung wala man lang heat generation, so pwede mo man lang na siya ma-zero, pero it should be there in the equation. So the energy balance equation for any particular material will be this: the rate in which the energy is changing, or specifically the rate in which the total energy of the object or the material is changing, is equal to, by the way, it's also written here, the rate of energy generated or generation, the rate of generation, the rate of heat transfer that is entering the system or your body, the rate of heat transfer that is leaving your material, and you can account as well the initial total energy of your system minus the total energy of the system minus any work that is done by the system. So if your system does work, it has also to be subtracted from this particular set equation. Although, class, most of the time, inila ang ginabutang. Wala na ni siya ginabutang ang total energy, initial and final of your system, and any work that is done by the system. But if these three are stated in the problem, that you have released the initial total energy of the system stated, the final total energy of the system, and any work that is done by the system, then you are to place it in this formula. What will you do if nothing is mentioned about this? It's automatic then that these are the same. This initial total energy and this total energy of the system final might be the same. So they might not be as well written. The same thing if there's no mention about work, then we take away work there. Meaning your system is not doing any work at all. Or if it's a chemical reactive system, if the system does not do any work, then this will also be zero. Okay, you will revisit this energy balance equation again when you go to your chemical reaction engineering in the second semester, because we will again set up the same energy balance equation. The heat generation part in here will be due to the generation of energy in the process of reaction. Okay. So this actually gives you already the entirety of the introduction to heat transfer. And in relation to this, I have placed in Canvas things that you need to ask. You need to rather do, or tasks that you need to do. The things that I have written here is just but a summary of what is written on tab. So a short discussion of everything that I have discussed in detail on top. These are the references, and these are the online resources where I took. I think the summary, I took it online, because if it's an elementary or if it's a senior high student, if it's just introduction to heat transfer, they would more or less grasp it if it's presented in this manner. Very simple manner only. Okay? Now, since we're done here, do you have any questions? Let me go back to, you have any question, class?
None, miss.
None. So
None.
here naman. Sige, so you start working on the task that you are to answer there, because those tasks will require you to think and will require you also to read, because I think in one task there you have to read something. I'm not sure because I have already 4 subjects in mind, so I'm not sure if I gave you a reading task. Okay, so kung wala man lang question, what happens next is today is Wednesday. Supposed to be this afternoon if this is not if this is not orientation week. You will already have your dry lab in the afternoon, 1:30. So you will only have your lunch break, 1:30 to 4:30. Wherein if there were exercises that I place in Canvas, you will have to do them and submit them also at the end of the 3-hour period. But for now, you can use it in doing the tasks that are set for you to do in Canvas. That way, even if their deadlines are not today, even if next week, you are already free, because we still don't have anything to solve for now because we're just on the intro part. Do you get it? I will update your Canvas as to your schedule. So I mentioned ko na kayo na. So I will update the synchronous time. Definitely we'll see each other there. And the asynchronous times, which we may use or may not use, depending on the need, and the dry lab schedule, which will really require you to solve on your own because it's dry lab. That is why it's not appearing in your schedules. It will require you to solve problems related to what has been discussed during the synchronous discussion. So if there are no more questions, I will stop sharing for now. And I'll stop recording.